ਹੈਲੋ ਡੀਅਰ ਸਟੂਡੈਂਟਸ, ਅੱਜ ਦੇ ਇਸ ਅੱਜ ਦੇ ਇਸ ਲੈਕਚਰ ਦੇ ਵਿੱਚ ਅਸੀਂ ਗੱਲ ਕਰਾਂਗੇ ਦੀ ਅਨਦਰ ਐਪਲੀਕੇਸ਼ਨ ਆਫ ਕੈਨੋਨੀਕਲ ensemble and in this we will discuss about the paramagnetic problem कि when system behave as a magnetic dipole in the canonical ensemble and how we can find out the partition function of such problems. So in this, consider a system of n magnetic dipoles, each having some magnetic moment, suppose mu. So before starting the article, I would like to tell you what is the magnetic moment. So magnetic moment of a magnet is the quantity that determines the force that magnet it can exert on the surrounding particles, or suppose if we are talking about the identical system, so the one magnetic dipole system, how it is exerting force on the another system, and due to this force the torque that a magnetic field will exert on the another magnetic dipoles, and we have to find out that torque, and from that we have to find out the total energy of the each dipole, and from that we can find out the partition function. Now this magnetic dipole in the presence of external magnetic field, so here we represent mu as the magnetic moment of dipole, and this magnetic dipole it is present in the magnetic field. So this H it is generally represented as the external magnetic field. So due to the presence of this external magnetic field, the dipoles it will experience a torque. So due to this torque, it will tend to align all those dipoles in the direction of that magnetic field. Now if there is nothing to check this tendency, then all these dipoles they would align themselves precisely in the direction in which we have applied this magnetic field. So we would therefore achieve a complete magnetization of this system. So if we are continuously supplying this external magnetic field, and at the end, so when the thermal equilibrium is achieved, so we have a ensemble that is having the complete magnetization of all the system. But in reality, however, these thermal agitations or due to these collisions between these electrons or the particles which are present within these dipoles, so these thermal agitations in these systems they offer some resistance to the tendency of magnetization, and in equilibrium we obtain only the partial magnetization. So there is a difference between this complete magnetization and partial magnetization. Now this actually it is completely dependent upon this temperature. Now as the temperature of the ensemble it limit to 0 Kelvin, and in this case these thermal agitations they become ineffective, and our system it exhibits a complete orientation of the dipole moment, so along the direction of the magnetic field. So whatever is the strength of this magnetic field, so as we are so at a temperature of 0 Kelvin, so where we have nothing to consider any type of thermal resistance or agitations due to these collisions, so at this temperature our system it has complete magnetization. Now as the temperature we are increasing and the temperature it approaches infinity, so in this state so we approach a state of complete randomization of these dipole moment. So why these randomization? Because during the temperature which is very high, so there will be lots of thermal agitations, loss of thermal loss, and due to the large number of collisions, So it is very hard to achieve these complete magnetization. So this state we generally consider as the complete randomization. So where the magnetization it is negligible small. So this complete randomization implies a vanishing magnetism, and so we generally consider the case of our canonical ensemble at some intermediate temperature. So the temperature which lies between 0 to infinity, so at some intermediate temperatures. So this situation of magnetization, it is completely governed by a quantity which is dependent upon mu h over kT. So because the temperature it is being dependent upon this mu and h. So in this model of classical statistics, we will consider the particles as distinguishable. So particles or our dipoles, we will consider it as distinguishable, practically static, non-interacting dipoles, and freely oriented. So our dipoles, they are freely oriented dipoles. So such type of model or such type of problem, it is obvious that only energy we need to consider in this problem is the potential energy of these dipoles, which arise due to the presence of this magnetic field or external magnetic field, so which we have applied. And second, it depends upon the orientation of these dipoles, so that is the magnetic moment of the dipoles. So the energy or the potential energy of these dipoles, so it is dependent upon summation of I1 to n, where I represent the number of identical magnetic dipoles which are present, and mu I, that is the magnetic moment of dipole, dot h, so that is our external field which we have applied. So this equation becomes minus mu h summation of I1 to n. So this is a dot product, so mu h cos of theta I. So theta I is showing some sort of orientation of the dipoles, and at what angles our dipoles they get oriented due to these external magnetic field. So that is represented with this theta angle. So let us say this is equation number 1. Here, so in this case, we neglect the effect of induced magnetic field because we have considered that the dipoles which are present within the ensemble, they are non-interacting. So we have neglected the effect of induced magnetic field which will be generated due to these magnetic moments. So the partition function of the system, it is generally written as Qn, so which is dependent upon this beta factor, that is temperature, summation of theta I, exponential of minus of beta into h. So this is how we write our partition function. So here h, that is our Hamiltonian, and we generally represent this Hamiltonian in terms of potential energy. So here we will write it as beta into E. So this equation becomes summation of theta I exponential of, so E is minus mu h cos of theta I, so this minus sign it get cancelled, beta mu into h summation of I1 into n into cos of theta I. So here this Qn, that represent the summation of all set of orientations of all those identical dipoles. So it is something like we can represent it as orientation of theta 1 for first dipole, So and so for Q1 dipoles. So similarly, so this orientation it can change. So there will be number of sets which we can make. So from such orientations and so many sets so will be formed. So this is summation. It is a summation over all the sets of orientation of this system, and we can write this equation number 2. So let's give a number. So this is our equation number 2. So we can write this equation something like summation of sets of this theta and pi of I1 to n exponential of mu beta h cos of theta I, so that we can represent as summation of 1 to n, and this is the summation of all those theta of n exponential of mu beta h cos of theta I. Or we can also write down the partition function of all those n-identical magnetic dipoles systems which are present in the ensemble. So that is Q of 1, that is partition function of one dipole raised to power n identical dipole. So here Q1 beta, so that is representing the single partition dipole, single dipole partition function. So Q1 we can write from this above equation something like Q1 of beta, so that is summation of theta exponential of beta mu h cos of theta. So if the magnetic field, so that is the value of h, the external field we have applied in the z direction, then mean magnetic moment of this system it will be in the direction of field. So it is something like, just a minute, so let me erase it. So if we have, this is our x-axis, this is y, this is z-axis, and if our field that is applied h along the z-axis and dipole it will have some orientation along this theta, and the value of this mu of cos of theta, so it will be parallel to this aligned along the direction of magnetic field. So the value of mu of cos theta, so it will be along the parallel to magnetic field. So this magnetization, so which is a parallel along the direction of z axis, so that is known as the magnetization value of magnetic dipole. So this magnetization, so which we generally represented as MOZ, so that is summation of I1 to n, so into mu of cos of theta I. So this mz we can find out, and from that we can find out these various thermodynamic statistics. So let us solve this equation further. So this equation we can write it as mz, that is summation of I1 to n mu of cos of theta I. So this we can write it as 1 over beta curly by curly of h, and taking log of n partition function. So this we can also write it something like that 1 over beta curly over curly of h log of q1 partition function of one dipole raised to power n. So this n, it comes in the power of this ahead of this logarithmic value, or we can write it as n over beta curly by curly of h log of q1 beta. So taking the value of this curly by curly of h, so this equation becomes n over beta, so logarithmic of the partition function of one dipole, so that is exponential of mu bh cos of theta. So this equation becomes beta into mu of cos of theta. So beta and beta get cancelled. So what we are left with is n into mu of cos of theta. So this is the value of the magnetization. Now this we can relate something like the number density function nr, which we have find out in our starting lecture. So that is equal to the probability function pr multiplied by nr, that is the number of identical systems. So similarly we can write this mu of cos of theta something like summation of p theta into mu of cos theta, and from that we can write the probability or the relative probability factor p theta, which is exponential of minus b into e theta over the partition function, that is summation of exponential of minus b into e theta. So the denominator, which is in this case, so that is generally known as the value of partition function for one dipole, and if we take the logarithmic value of this, so let us say this is our equation number 3 and this is our equation number 4. Now if I take the logarithmic value of this q1, which is summation of exponential of minus p into e into theta, so theta, that the energy, it is dependent upon the orientation, so which is due to mu and our external magnetic field h. So taking log of this single dipole partition function, so this is exponential of minus p into e theta, and from that if I take the derivative of this term log of q1 beta, so this I can write as log of summation e raised to power minus be into theta. So here E we know that is equal to minus mu h cos of theta, and if I take the derivative of this curly e theta by curly h, so this will be equal to minus mu into cos of theta. So this equation I can rewrite something as, if I take the derivative of this logarithmic value, so this comes in the denominator exponential of minus b into e theta, so minus of beta and summation of exponential of minus b into e theta, and the derivative of this e, which is also a function of h, so we also need to consider as curly by curly h of e theta. So putting the value of this curly e theta over curly h, so here, so this equation, so here minus of beta, here minus sign, so both get cancelled. So what we are left with is beta into summation of exponential of minus b into theta into mu of cos theta over summation of exponential of minus b into e theta. So this is again our probability density factor. So putting the value, so this equation becomes summation of p theta into mu of cos theta. So this is curly by curly h log of q1 beta. So if I move this beta to the left hand side, so this equation becomes 1 over beta curly by curly h of log of q1b. So that is equal to summation of p theta into mu into cos of theta. So this p theta into mu of cos theta, the value of this summation of p theta, so which is considered as 1, so we can write it as log of q1 beta, so which is equal to mu into cos of theta. So we need to calculate the degree of magnetization of this system. So in order to find out the relation between this magnetic potential energy and these thermal potential energy, and how these mu h and kt, so they are exchanging their energies, and due to that these it is affecting the magnetization of the system. So we need to drive a connection between these two terms. So for that we need to calculate the single dipole partition function, so by considering the solid angle as well. So here now we will also introduce the use of this sine theta d theta into d phi. So for the elemental solid angle, which is representing a small range of orientations, so which the dipoles they are considering along some solid angle d phi. So the value of this modified partition function of q1 beta, so this we can represent as, because this solid angle it is from 0 to 360, so we will take integration along this 0 to 2 pi, and due to this d theta, which is can be from 0 to pi, and the value of this total exponential function, which we can write it as beta mu h cos of theta uh, into sine of theta d theta into d phi. So this equation, if we remove this integration and by writing it as 2 pi 0 to infinity 0 to pi exponential of beta mu h cos of theta, something like sine theta into d of theta. Now we have to solve this integration, and suppose if I put cos theta as x, so in that case, so when theta is 0, so when we know that cos of 0 that is equal to 1, so at that time, so x will be equal to 1, and if I take the derivative of this cos theta, so that is minus of sine theta into d theta, which will be equal to dx, and now in this case if I put theta is equal to pi, so at that time, so x will be equal to minus of 1. So this theta, which is varying from 0 to pi, and at that time the range of this x, it is being changed from 1 to minus of 1. So I can write this equation q1 beta as, because here this minus sine theta into d theta, so that will be equal to dx. So I will write it here minus of 2 pi. So this 0 to pi limit, so it is being changed from minus 1 to plus 1 exponential of beta mu h cos theta, which is equal to x into dx. So this is our modified equation. So let us say this is equation number 5, this is equation number 6. So this equation I can write as q1 beta, which is equal to 2 pi from minus 1 to plus 1 exponential of beta mu h x into dx. Now let us solve this integration. So this comes out to be 2 pi over beta mu h exponential of beta mu h minus of minus exponential of minus beta mu h. So we know exponential of beta mu h minus exponential of minus beta mu h over 2. So that is our sine hyperbolic function. So this equation becomes 4 pi sine hyperbolic of beta mu h over beta mu h. So once we find out this modified expression of this partition function, from that we can find out the value of this magnetization, which is along the z-axis. So that equation we have already found, that is n over b curly of curly h log of partition function of this one dipole. So putting the value of this partition function q1b in this differentiation, so this equation comes out to be n over beta curly by curly h log of 4 pi sine hyperbolic beta mu h over beta mu h. So when I further solve it, so this mz, so we can write as n over b curly by curly h. So log of 4 pi sine hyperbolic beta mu h. So the terms which are in the denominator, so we can write it as minus of log beta mu h. So opening this logarithmic terms, so this equation we can write log of pi plus log of sine hyperbolic beta mu h minus of log of beta mu h. So log of pi, that is 0. So this equation, taking when we open this derivative, so curly by curly of h log of sine hyperbolic beta mu h minus curly by curly h log of beta mu h. So this what we get is n over beta, so derivative of this logarithmic term, so this comes out to be 1 over sine hyperbolic beta mu h. So derivative of a sine hyperbolic, that is cos hyperbolic beta mu h into the term which is within this bracket, that is mu into b. Similarly we can write it as mu b over derivative of logarithmic term, that is mu m h. So this mu b, it is a common, so we can write this as n over beta into mu, so they get cancelled. So cos hyperbolic over sine hyperbolic, so that is our cot hyperbolic beta mu h minus 1 over beta mu h. So this is what we get for the mean magnetic moment of one dipole moment. So for one dipole, so this is the mean magnetic moment, and similarly for the n dipoles, so we can find out So mean magnetic moment of n dipoles, so which we have considered, because here we have written the term n into b. So this is our magnetic moment of n dipoles. So for n identical dipoles which are in the canonical ensemble. So this we have represented as m of z, and similarly we can write the magnetic moment of one dipole. So if I divide this with n, so this we generally represent as mu z bar. So this mean magnetic moment of one dipole, so that we can write as mu into cot hyperbolic beta mu h minus of 1 over beta mu h. So this we can write as mu z bar, which is mu into cot hyperbolic x minus 1 over x. So this function mu z we can write as mu of Lx function. So this Lx is called the Langevin function. Langevin function, and we generally represent this Langevin function as cot hyperbolic of x minus 1 over x. So because this is the same equation which we are getting, so we have considered here the value. So this is our Langevin function. So x which we have assumed here, so x is beta mu h. So this we can represent as mu h over kt. So this is quite important term. So mu h, that is representing the magnetic potential energy, so which is being exerted by these magnetic dipoles when they are passing or they are aligned along some external magnetic field, and kt, that is our thermal kinetic energy, so which is hindering the movement or the magnetization of these magnetic dipoles. And as the temperature it is being increased, so the thermal agitations, they hinder the value of this mu h, and due to that we get less magnetization of the system. So the parameter x, it measures the strength of potential energy, and it compares the value of this potential energy, so with respect to thermal kinetic energy. So the magnetization of system, so it is, we can write, that is mean magnetic moment of one dipole over unit volume. And if there are n dipoles per unit volume, then the mean magnetic moment, which we generally write it as mz, so which is n into mu z bar. So mz, so that we can write it as n into putting the value of this mu z bar, so that is equal to mu into this Langevin function. So from that we can check from this Langevin function, so how the magnetization of this system, it is being changed with respect to change in value of temperatures. So let us do some cases. So case 1 is when magnetic fields are too strong or very much strong, so it will be at low temperature. So at low temperature the value of x, it will be very large as compared to 1. So because X we know that is mu H over KT. So at low temperature this denominator term it will be very small. So the value of X it is that the value of this mu H it is much greater as compared to KT. So in this case when X it is much greater than 1, then the Langevin function, so it is considered as having the maximum value. So at this state the system acquire the state of magnetic saturation or complete magnetization. So that is complete magnetization. So mu z that we can generally represent in this case is equal to mu, and mz that will be equal to mu into n. So second case is, so as we increase the temperature, so when the temperature it is very high, so in that case the magnetic field will be very weak. So in this case the value of this mu h it is very less as compared to this thermal kinetic energy kT. So the value of x it is very less, and in that case our Langevin function we can write it as x over 3 minus x cube over 45 so and so. So for first order, so we can write it as Lx which is of the order of x by 3. So in this case our mz, so which we can write as minus n mu x over 3. So putting the value of this x, so this becomes n mu square h over 3 kt. So this x or this Langevin function it represents how the system behaving with the change in temperature. So we derive a term that is the high temperature susceptibility. So this high temperature susceptibility of this x eta it can be given as the limit of h it approaches 0, so curly mz over curly h. So in this limit, so n mu square over 3 kt. So here c, so this eta value which comes out to be c over t, or this susceptibility it is inversely proportional to temperature, and this c it is equal to n mu square over 3k. So n is the number of identical system or number of identical dipoles which are present, and this c that is known as the Curie temperature or Curie constant. So this x which is c over t, so this is the famous Curie law of paramagnetism, and which represents how the potential energy of these magnetic dipole it is being affected or it is being varied with this thermal agitations or this thermal kinetic energy. So this is all about for today's lecture, and in this we have discussed about the detailed classical treatment of paramagnetic problem, and in our next lecture we will treat this same problem using this quantum mechanical concept, and in that we will discuss how these total angular momentum it is being changed, or how the spin of these particles or these magnetic dipoles it is being affected when we are keeping these magnetic dipoles in some external magnetic field. So okay dear students, if you have any doubts you can write in the comment box, or you can also ask me through WhatsApp groups. So see you in the next lecture. Till then, goodbye.